Rates of change, guys, a very crucially important part of differential calculus. So let's have a go at this. It's very, very interesting. We deal with rates of change all through our lives. So let's have a good look at it in terms of differential calculus, and we will nail it. Rates of change are, in terms of a mathematical sense, okay, they are either gradients. This is the first thing they are. Gradients, e.g. the average rate of change of one variable with respect to another. Okay, now I've got a y here, I've got an x here. Now between point 1 and point 2, even though this black graph is curvy, the average rate of change between point 1 and point 2 is simply just the rise over the run between those 2 points overall, without any consideration at all of what happened in between here. We just consider where we are there, and we say, well, okay, what's the rise? It's y2 minus y1. What's the run? It's x2 minus x1. Therefore, the average rate of change of y with respect to x between those 2 points basically is that, right? It's the rise over the run. Now, or they are gradients there, or they are derivatives, and that gives us the instantaneous rate of change of one variable with respect to another at a point. Okay, so we have gradients which give the average rate of change between 2 points, or we have derivatives which gives us the instantaneous rate of change of one variable with respect to the other at a single point. At a single point, right? That's what they like. So therefore, see that? That is the that there is the the gradient of that green line, that tangent line there, basically gives you the instantaneous rate of change of one variable of y with respect to x, okay? And it's the same thing as the instantaneous rate of change at that point, okay? That's the derivative. So dy dx at p is equal to the gradient of the tangent at p. Yes, that's really important that you get that. Okay, if you just do the gradient between 2 points, you've got the average rate of change between those 2 points. If you do the derivative, which is the same as the gradient of the tangent at a particular point, and then sub the value of x in at that point, you'll actually get the numerical value of the instantaneous rate of change of y with respect to x at that point, right? Now, rates of change with respect to time, right? With respect to time, so you haven't got x here, you've got t there, if you like, which are frequently used are velocity, which is the rate of change of displacement with time. Okay, so if you had displacement as x, it would be dx dt as an instantaneous rate of change of x with respect to t, all right? Or it would be x2 minus x1 over t2 minus t1 as an average rate of change between 2 points. You get what I'm saying, don't you? Yes, and the displacement, in case you're not sure of that, the displacement is the position relative to a fixed known point, e.g. the origin, all right? Now, speed is another one. Speed is different from velocity. Speed is just basically the rate of change of distance. Now, distance is different from displacement. Distance is just the total length of your journey, whereas displacement is actually where you are relative to where the fixed reference point is. Okay, so that you could actually go from home down to the shopping centre and back on a shopping trip 5 kilometres away to the shopping mall, and you would find that your distance would be 10 kilometres there and back, but your displacement after you get back compared to where you started as a reference point, home would be the reference point, the displacement would be 0. Okay, that's the difference between displacement and distance. Flow rate's another one. Flow rate is a rate of change of volume with time. Okay, so this is what we're talking about when we talk about rates of change. And the common ones in life that we use are these kind of things, yeah? Rates of change with respect to time. Okay. Now we're going to do some examples now. Alright, we've got a balloon. And unfortunately, this balloon's developed a microscopic leak. And it will therefore decrease in volume. Okay, the volume of the balloon is going to go down because it's going to deflate. So its volume V apparently is defined by this equation. Good heavens above. So T is time now, and T, of course, time has to be greater than 0. Can't be negative. So we're going to find the rate of change of volume after 10 seconds and 20 seconds. That is the instantaneous rate of change of volume. So what's that, guys? That's dV dt. Then with 10 seconds substituted in, 20 seconds substituted in, and then we have to find out for how long could the model be valid. Well, I suppose that means when V is greater than or equal to 0, I suppose. Do you think so? Because V can't be negative. How could you have a negative volume? That wouldn't make any sense. Okay? Alright, let's go for it. A1, so V is that now. We've got to do the instantaneous rate of change of V with respect to T, which is dV dt, isn't it? And that's easy to do, isn't it? Right? Do you agree? Minus 10, and that'll be minus 100, 1 over 100 I mean, times 2T, or minus T over 50 after you do the cancelling. Now, we substitute, first of all, T is 10, don't we? Right? You get that? So that's minus 10 minus 1/5, which is minus 10 and a fifth, which would be minus 51 over 5. And that'll be, I always like to put the units in. They don't seem to be too fussy about that in the exams, though. So, but I like to put it in because it's just nice to know. It'll be centimetres cubed, and is it seconds? Yeah, per second. And you see the minus? The minus tells you it's going down, right? It's decreasing. It's a negative rate of change, which means the volume's decreasing. Righto, A2 for me and you, woohoo. T is 20, yeah, go for it. And we got that, minus 10, yeah, okay, that's fine. That gets us minus 52 over 5 centimetres cubed per second. Alright, that's A done. Here's B now. The model remains valid while V is greater than or equal to 0. Of course it does, yeah? So we've basically, what about if we... So you can see that the original volume of this thing when T is 0 would have been 600, right? So we want the V to be from 0 up to 600. That's when the model's going to be valid, right? So why don't we just work out the time at which V is 0, and that'll get us the time interval over which the model is valid. You get what I mean? So I'm going to substitute V as 0 into that equation, and I'm going to try and solve it for T. Looks like a beast. So if we, oh goodness gracious, I've multiplied by 100 and I've got telephone numbers here. Good heavens. So therefore, if I just turn it around to positives, which I like to do, by multiplying both sides by minus 1, I'll get that, won't I? But I don't think I can't get my head around how to solve it. I think I have to use the quadratic solution, which I do. And I think, look, this is time for the calculator to come and rescue me. I'm in big trouble here. My head is splitting. There you are. Hello, Mr. Calculator. Solve that thing. I used X's, but I'm just used to using X's on the calculator, but it gets to the same thing. And I got this stuff. Goodness. Well, so what does that look like? X is minus, well, see, it's really T, guys. It's T, it's time. That doesn't make any sense, but that certainly does. 56.7764 seconds for T. That would make sense, wouldn't it? That's the one. So it looks like it's valid for T. T had to be greater than 0. They told you that. Don't go putting equals 0, because this question says T has to be greater than 0. And I would say, look, you could either say less than, probably less than, or less than or equals to 56.78, right? I don't know that it really matters too much. It depends on how you define whether the model is valid when you actually have 0, or whether you say the model has to be valid when V is only greater than 0, yeah? Yeah, so that'd probably do. I think both of those would be marked correct, whether you had T goes from greater than 0 up to less than 56.78 or less than or equal to 56.78. I think it's fine. Yeah? Okay, goody. Let's go and do another one. We've got a point. This looks like a kinematics one now. A point moves along a straight line so that its distance x centimetres from the point O, or the origin, at t seconds, centimetres, is it? Yeah, I like to get the units right. Is given by the formula x is this stuff. It's a cubic, isn't it? Find at what times in what positions it'll have zero velocity. All right. And its acceleration at those instants and its velocity when the acceleration is zero. That's right. Look, this is just derivative land, guys, because the derivative of this is really, when it says distance here, this is really position. You know, it's position in relation to this point here, right? Which position is another name for displacement. All right. Now, the derivative of displacement is velocity. The derivative of velocity is acceleration. You have to know that, guys. You really, really have to know that. Okay, so let's just go with this and work it out. Okay. A. Now, what do we do? At what times and in what positions will we have zero velocity? Yeah, well, we have to work out the velocity first. So, therefore, the velocity is dx dt, as I just said. That works out as you take the derivative of that right-hand side, you get that. Now, zero velocity, so we've got to set that equal to 0, okay, and solve it for t. There it goes. Now, I think we need to divide through by 3, don't we? Yes, very good. That's easy to factorise as whole numbers, you get that. So, therefore, t would be 1 or t would be 3. Yes? Now, they're the times. We've got to get the positions now. So, you would substitute these values of t back into there to get what x is at those respective times, right? So therefore, that's when t is 1, I mean, plus 4, that's 4 centimetres to the right of the origin. That's what that would mean. And when t is 3, you'd get that, which looks like, oh, it's right on the origin when t is 3, isn't it? Right? That's very good. So zero velocity, just summarising, putting Mr. Box around everything. When t is 1, x is 4. When t is 3, x is 0. Hello, Mr. Box. I hope you're well today. He can't answer. But he's very well. Now, righto, so that's that. That's A done. Now, the acceleration, all right, that means now acceleration is the derivative of the velocity. So we've got to go do another derivative now, but on the velocity. So, yes, now what was the velocity again? I've called the velocity v, so we don't get ourselves into a big knot here. So therefore v was this little beastie here, dx dt is v. 3t squared minus 12t plus 9. So let's work out dv dt. That's a, it's the derivative of this thing, right? Is that 6t minus 12? It is, isn't it, right? So what are we trying to work out again? The acceleration, yeah, when t is 1 and when t is 3. So just plug and play now, guys. When t is 1, a will be minus 6. When t is 3, a will be 6 3s are 18 minus 12, which is plus 6. That's interesting, isn't it? Okay, so we've got that done. We've just done B. Now, what's C? The velocity when the acceleration is 0. Okay, we just have to set the acceleration equal to 0. That's easy. And we'll get t. T will be 2. And then to get the velocity when t is 2, we have to substitute this value of t is 2, into the velocity equation, this one. Yeah? So there you go, there you go, there you go, and there it is. Minus 3 centimetres per second. Okay, you got it? We've done it. We just did the whole thing, the whole shooting match. Yes, you pleased? Give yourself a pat on the back. Now this last one, just to finish it all off, another kinematics one. This has got a little bit of anti-differentiation in it, which if you don't know how to do yet, don't worry about it. Just gloss over it, and you'll come to it sooner or later. That's in part C. Yeah, so don't worry if you don't understand what I'm doing. I'm just going to do it anyway because it's a typical kinematics question. Part A. Now what have we got here? A particle starting from the origin has a velocity of v equals 2t minus 4, where t has to be either, can't be negative, and t is measured in seconds when x is measured as a displacement from the origin in centimetres. Find the initial velocity. That's easy, guys. We've got the velocity, the rule for the velocity here. V is 2t minus 4. Substitute initial means when t is 0, guys. So you substitute t as 0 and you'll get minus 4. Minus 4 centimetres per second is our answer. Okay, that's good. Now, B coming up. What's B? the acceleration, this acceleration, I'll find the formula for the acceleration and show that it is constant. Okay, well, acceleration is a derivative of velocity. So a is dv dt, and that's going to be, oh look, that's easy. It's the derivative of this with respect to t, which is just 2 centimetres per second, right? It's the derivative of velocity with respect to time. So it's centimetres per second every second, if you know what I mean. Centimetres per second per second. That's how you write it. 2 centimetres per second squared, or 2 centimetres per second per second. No, I haven't got a speech impediment. It's just the way it works, and that's constant. Yes? Right, now we've done that. So that's B done. Now C is where we have to do a little bit of anti-differentiation, because in order to get the formula for displacement, you have to do the reverse of differentiation, which is anti-differentiation. The antiderivative of velocity is displacement. So just go with me. If you know what I'm doing, good. If you don't know, just go to sleep for a minute, and you'll get it sooner or later when you get to anti-differentiation. So that's V. Now the displacement is the antiderivative, or the thing which gave rise to this as the derivative, right? Because the derivative of displacement is in fact velocity. So I'm doing the reverse process. I'm going back to the original parent function which gave rise to this as the derivative. So that'll be t squared minus 4t plus some constant, which we have to, that's called the constant of integration. Now, in order to work out what the constant is, this little beastie here, we have to substitute our values in, because we know that it had starting from the origin. Didn't they say that? Yes, starting from the origin, which means when t was 0, x was 0. That's what that means. That's actually a clue. Yeah, it's a clue. So we substitute here, this is 0, this is 0 to get the value of this. And therefore C is going to work out to be 0 anyway. Therefore now I've anti-derived, and I've got my rule for displacement in terms of time. So now we can do part C by substituting t as 2 into that rule, and you get that, and that's going to be minus 4 centimetres. So it's 4 centimetres to the left of the origin when t is 2. Okay, the minus, you need to put that minus in. That signifies on a number line that you have 4 centimetres to the left. But minus 4 centimetres is a correct way of representing that. Yes, we use minus and plus to do our sense of direction relative to the reference point, which in this case is the origin. Okay, what's D? The average velocity. Now this is really important, and this one here is a booby trap, right? This is always a booby trap, this average speed stuff. So let's do this first. The average velocity over the first 3 seconds. Now do you see that word average? Average is not instantaneous. That is just the gradient, or the rise over the run between t is 0 and t is 3 of displacement versus time. Right? You have to get that. You have to know. So I'm working out the displacement at 3 seconds minus 3, and I'm working out the displacement at 0, which is 0, because that's what they told us. It started from the origin. And now, watch this. The average velocity is just the delta x over the delta t, right? In a macro sense, just the finishing value of x minus the initial value of x over the finishing value of t minus the initial value of t, and that's what you get, right? That's the average velocity. So that looks like it's minus 1 centimetre per second. Now, this is the beast, the average speed. When they ask you these average speed questions, you have to be extremely careful, because the chances are this particle will have changed direction within the time span that they're asking you for the average speed of. First 3 seconds. So I'm telling you, I would, if I was a betting man, I would bet, which I'm not. I'd bet you though, as a fun thing, that it's changed direction. Therefore, if you want to get the distance that it travelled, you have to know how far it travelled one way and how far it travelled the other way, and add them up, because distance is different from displacement if the thing changes direction in the middle of the time span that you're interested in. So average speed Average speed is the total distance, not the total displacement. No, the total distance over the total time. And I always like to draw a velocity versus time graph just to represent what's going on. You know that v was 2t minus 4. So I draw the graph of 2t minus 4. It's got an intercept here of minus 4 and a gradient of 2. So that shows you guys, look, that the velocity was negative from 0 to 2 seconds. And it was positive, right? Positive up here. Positive from 2 seconds onwards. So therefore, if you like to visualize this little beastie, what it's doing, you could imagine it going backwards from t is 0 down to t equals 2, and then it starts going forwards from t is 2 onwards. So you've got to get the two separate journeys, the backwards journey, the total distance of, the forwards journey, the total distance of. Strip away any minuses or pluses, because you only care about distance here. Add up the two lengths of the journeys as a total aggregate length of journey, and then divide it by the 3-second time interval that we're interested in, right? So we need to find the distance from t is 0 to 2 and the distance from t is 2 to 3, and I'll show you. When t is 0, x is 0. When t is 2, x was minus 4. Now, here we go, look. I've tried to show you on a number line. See, when this is the first bit of the journey, the distance from t is 0 to t is 2 is minus 4 units. There. Now, that's the displacement, but the distance is just 4, because the distance doesn't have any plus or minus, it's just a length, right? Now, for the second part of the journey, when it started going forwards, when t was 3, x was, what is it, minus 3. So it's actually travelled from t is 2, for that 1 second where it started going forwards, from t is 2 to t is 3, it ended up at minus 3. So it's gone 1 unit back in this direction. Positive, right? So you watch. That's what it did. It went from there to there, a distance of 1 centimetre. 1 centimetre, right? So now what is the total distance? The total distance travelled is this 4 centimetres backwards, or to the left, plus this 1 centimetre forwards to the right, which is 5 centimetres, right? This is not the same as displacement. It's distance. So therefore the average speed is the total distance over the total time, which is 5 over 3 centimetres per second. That's different. I think the average, what was the average velocity? Let's just go back and have a look. What was it? The average velocity was, it was minus 1. See, that's on the previous screen, by the way. I've just gone back to the previous screen. See, it's different, isn't it? It's totally different. So you have to be very careful of that. And that's the end of this question, and the end is our friend. The end is our friend, and you're a star. You'll go far. You need to practice these things to get good at them, and just be very, 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 very wary when they ask you average speed questions, because they're the ones with the booby traps in them. All right? Okay, you're a star, and go and practice and get really good at them, and have a wonderful day, and I'll see you anon.